So with our snow day on Friday, we didn't quite have a chance to finish up section 2.6. So there's just one little bit at the end that I do want to talk about in this video, so we don't have to take as much time leading into the week after spring break, since we still have to get through 2.7 before the pretest. And that's just solving inequalities with polynomials. And really, we have worked with this actually before when we talked about inequalities with quadratics. It's very much the same idea. Now we're just going to take that idea and apply it to all types of polynomials. So what we had looked at before with a quadratic function, right, something like this. Say here's our quadratic function f of x. We could visualize that with a parabola. There we go. We can visualize that with a parabola, and we would want to answer the types of questions like when is f of x less than or equal to 0, for example. And what we essentially did to solve that is we graphed it and we looked, okay, well, here's the x-axis. This is when it is equal to 0. And this, in between those 2 points, is when it's below 0 or less than 0. Or on the other hand, if we wanted to say, okay, when was f of x greater than 0? Well, that's going to be whenever it's above the x-axis. So that's from like this point to the right or from this point to the left. And we can use the visualization of a graph to understand these inequalities and to solve these inequalities really effectively. And we can do a pretty similar thing with any polynomial. So for example, if we graphed a polynomial that looked like this, where we had something like this, say, right, we can look at this graph and see, okay, it's pretty clear that from this point to the right, our function p of x is always going to be greater than or equal to 0, and our function from this point to the left is always going to be less than or equal to 0. So we can, again, just like we did with quadratics, if we want to graph the function out, we can visually see, okay, when is this greater than or above the x-axis, and when is this below the x-axis? But we can actually make it even simpler for ourselves, because what this process is really boiling down to is identifying on the graph where the x-intercepts are and then seeing how it behaves when it's above the x-axis or below the x-axis. And all of the tools that we've sort of worked with in this section have kind of built up to us being able to do that. So we have this idea now of the x-intercept is when f of x is equal to 0. So that x value is going to make our polynomial equal to 0, and that is also a root of our polynomial or a factor of our polynomial. And we spent most of this chapter, or a big chunk of this chapter at least, talking about how to find those roots. Okay, and then once we find those roots, it's just about understanding what is happening in between, right? So in this case, like what happens between, here's, we'll say, I'll call this one x1, I'll call this one x0, right? What happens between x0 and x1? Well, that graph, that part of the function is positive, so it's above the x-axis. So we can say that that's greater than 0. We also have understanding now about how to determine the behavior of a graph at any given intercept. We also have the ability to determine the behavior of the graph at the endpoints. Does it go off to positive infinity? Does it go off to negative infinity, etc.? And we can use all of those tools to solve polynomial inequalities. But yeah, that's a lot of words. Let's put this actually into action and see what specifically I mean by this. So For example, we might be asked to solve the following inequality. Where we have x to the fourth minus 4x is greater than or equal to 9x squared minus 12. Okay, and as this looks right now, this seems like it's kind of really complex to solve, right? Because if we think back to when we did inequalities with linear functions, things that were written like 5x plus 3 greater than negative 5 or something like that, we could just very simply apply kind of the same rules of an equation, right, and just solve for x here, and that would be a way to find our solution to that inequality. We can't apply that same kind of thinking here, or at the very least it's significantly more complicated, but we can use the tools that we've done in this chapter to get there. So instead of trying to solve for x here, what we can do is we can manipulate this polynomial to get it in the form of like some polynomial greater than or equal to 0. So if I just swing these over here, I'll have 9x squared minus 4x plus 12 is greater than or equal to 0. Right, and now this guy here, right, this here is in the form of some polynomial, and we're trying to determine when is that polynomial greater than or equal to 0, or when is that polynomial above the x-axis on a graph, right? So our steps now are going to be to find the roots. When is it equal to 0? Okay, so I've gone ahead and done that, worked that out already, since we've already gone over the process of how to find roots of polynomials, and I don't want this video to be like 25 minutes long. So I'm going to just go ahead and factor that out for us. So this is going to be x plus 2 squared times x minus 1 times x minus 3. And we want to know when that is greater than or equal to 0. Okay, so if we wanted at this point, we could go ahead and graph this function. Right, so we know all of its x-intercepts because those correspond with the roots. They correspond with the factors. So we have a positive 3, a positive 1, and a negative 2. So I'm going to go ahead and fill those in on the graph. We've got a positive 3, a positive 1, and a negative 2. Okay, we know also that since this is a polynomial with an even degree, that either it's going to both go to positive infinity or both go to negative infinity. Since it has a positive coefficient, that means they both go to positive infinity. So our endpoints are going to, or our end behavior, I should say, at the end of our graph, not endpoints, but at the end of our graph will look something like this. And then looking at the rest of these roots individually, since this has an even power, at the negative 2 root, that means it's not going to cross. Since the rest of these, the other two, have odd powers, that means they are going to cross. So that will cross there just like that, and we'll have something like that. Now, of course, this is not trying to scale, but we get the idea, at least, of we can now look at this visually and say, okay, when is this greater than or equal to 0, and when is this less than or equal to 0? For our case, greater than. Yeah, we can see that visually now just by graphing it. Okay, so I can see that, okay, in this range here, in between these two roots, it's positive, so that will satisfy our inequality. To the left of this root and to the right of this root, it's both positive. So both of those intervals will also satisfy our inequality. So that's one way we can always approach these problems. We can actually break it down even simpler than that, though, by creating what's called a sign chart. Okay, so if we forget this graph for a moment, we can use that if we'd like to, but if we want to kind of shorten the process a little bit, we'll use what's called a sign chart. And essentially, what a sign chart is going to be is just a number line. So here's your sign chart. Okay, sign is in like plus or minus. So I can plot this like a real number line. And then wherever the roots are, I can go ahead and mark those off. So if this is 1, we have a root at positive 1, we have a root at positive 3, and we have a root at negative 2. Ooh, negative 2. So I'm going to go ahead and mark those off. Now, since we know that polynomials are continuous, right? We talked about this before when we talked about the intermediate value theorem, which I'm going to try to put a little link here in case you forget. But we've talked about the intermediate value theorem. We've talked about polynomials being continuous functions. Like simply put, you can draw them the whole way through without picking up your pen. But since polynomials are continuous, right, and we saw this in the graph that we had before, we can't ever go from being positive to negative or negative to positive without crossing the x-axis. So in other words, the only points that a polynomial can change sign, changing from positive to negative or changing from being greater than 0 to negative 0, is at these values here. So at these green lines or at the roots, right? It can only change from being above the x-axis to below the x-axis if it crosses through at an intercept. So at any point in this region, that means if this is positive, it has to be positive at all of the points in that region. And at any point in this region, if this was negative, then it would have to be negative at all the points in this region here. Okay? So we can use that idea and just kind of check a single point in each of these spaces to see, is it positive there, is it negative? And that will tell us the behavior of the function, at least as far as what its sign is, across the whole interval. So we can go ahead and do that. For example, if we looked at this interval right here, right? If we want to see the sign of our function, is it above the x-axis or below the x-axis from 1 to 3, we could plot or plug in 2 and see what that value is going to give us. So if we were going to do that, we would have p of 2 equal to 2 to the 4th minus 9 times 2 squared minus 4 times 2 plus 12. Okay, and when we do this, now we have 2 to the 4th, 16 minus 36 minus 8 plus 12. Hopefully I'm doing all this math right. And minus 36 minus 8 is going to be minus 44. 16 plus 12 is 28. 44 is greater than 28. So this is very clearly negative. So we can go ahead and mark a negative sign here. So because it's a negative value at 2, it's going to be negative for the entire interval from this root to this root, from this x-intercept to this x-intercept. And we can go ahead and check that at the other values too. If we plugged in like 5, for example, that falls within this interval here. That's greater than 3. So if we plugged in 5, and you can go ahead and try this yourself, but if you plugged in 5, you'd find that p of 5 is positive. And since p of 5 is positive, that means everything in this region is going to be positive. Okay, and then we can go ahead and plug in something from both of the other two intervals. So we could take 0, for example. if we plugged in 0, right, then we have 0 to the fourth minus 9 times 0 minus 4 times 0 plus 12. That's a positive number. So in this interval, we would have positive, right? So we've got p of 2 is going to be a negative number. We've got p of 5, we checked, is going to be a positive number. We've got p of 0. Oh, I don't think you can see that. We've got p of 0 is equal to a positive number. And we can check something like p of negative 3, which it turns out if you plug it in, that will also be a positive number. Okay, so we've got positive over this interval, positive over this interval, negative over this interval, and positive over this whole interval. Okay, and we can use that now to get our final solution. So if we want to determine when our polynomial is greater than or equal to 0, or in other words, when x to the fourth minus 4x is greater than 9x squared minus 12, all we have to do now is look at this sign chart. So it's positive here, that's greater than or equal to 0, or equal with the root, that is, but greater than 0 here, so that is the interval negative infinity to negative 2, and inclusive, since we have the less than or equal to, it is equal to at negative 2. Unioned with, so this is our solution here, unioned with our next interval, which would be negative 2 to positive 1, again including, since we have the equal to part. We're not going to include this since this is negative, but we will look at 3 and further. So 3 to positive infinity, and that will be our solution. And of course, we can reduce this, since these are both positive here, to just say, okay, this is negative infinity to positive 1, unioned with 3 to positive infinity. But this is going to be any of the x values that make this inequality true. Yeah, so that's pretty much it. If you have any questions about that, feel free to shoot me an email. Snowed in today, so got plenty of time to respond. But yeah, other than that, hopefully you have a good break, and I'll see you back next Monday.